All right, let's get into it. And don't worry, this isn't going to be a math class. Instead, we're going to pop the hood on the very technology that's shaping our world. I'm talking about everything from your phone to self-driving cars. We're talking about AI.
So have you ever really stopped to think about that? How does an algorithm actually learn? How does it go from getting pretty much everything wrong to suddenly recognizing your face or translating a whole language? I mean, it can feel like magic, right? But it's not.
The secret? Well, it's actually surprisingly simple when you break it down. An algorithm learns by finding the fastest, most efficient way to just get less wrong. Every time it makes a mistake, it measures that mistake, we call it error, and then it just adjusts itself, step by tiny, tiny step, to shrink that error.
Okay, so let's dive into that. This whole process of constantly getting better, it isn't guesswork. Oh no, it's a precision-guided journey. And it's powered by 3 fundamental ideas from calculus. So today, we're going to assemble a toolkit with these 3 ideas and see exactly how AI gets so smart.
First thing we need in our toolkit is a compass. You see, before an algorithm can even start getting better, it needs a destination. It needs a North Star to aim for. And in the world of AI, that destination is perfection. Or, as close as you can get to 0 error.
Now, this idea of aiming for a perfect destination is captured by a concept called a limit. And a limit is really just the value that a series of steps gets closer and closer and closer to. For our AI, that limit is the perfect state of 0 error that it is always chasing.
Let's make this real for a second. Imagine a military robot that's learning to long jump. On its very first try, it jumps 2 meters. On its second, 2.5. Its performance follows this pretty simple formula. On its nth try, it jumps 3 minus 1 over n meters.
So here is the million-dollar question. After 1,000 tries, or even 1,000,000 tries, can this robot ever jump exactly 3 meters? What do you think?
The answer is nope, it can't. With every single jump, that tiny fraction, 1 over n, gets smaller and smaller and smaller. So the jump gets closer and closer to 3 meters, but it will never, ever be exactly 3. That value, it approaches but never quite touches. That is the limit. And that's our compass.
All right, so our algorithm has its compass, and it's pointed straight at 0 error. But what's the best way to get there? I mean, there could be millions of possible paths. For this, we're going to need a steering wheel.
To get what our steering wheel does, just picture getting a speeding ticket. You tell the officer, hey, my whole 2,900-kilometer trip took me 72 hours, so my average speed was only 40 kilometers per hour. But the officer just points to the radar gun and says, yeah, but you covered that last 260-kilometer stretch in just 3 hours. Your speed at that moment was almost 90. See the difference? Average change versus instantaneous change.
That instantaneous speed is exactly what mathematicians call the derivative. It tells you the exact rate of change, the steepness of your path, at one single precise moment. It's not the average slope of the entire mountain. It's the slope right there under your feet right now.
Okay, so a derivative gives us an instantaneous measurement of change. But how in the world does an AI use that as a steering wheel?
Well, it uses the derivative to power one of the most important algorithms in all of machine learning, something called gradient descent. Think of the model's performance as a giant, hilly landscape. The hills are high error and the valleys are low error. The derivative tells the algorithm, right where it's standing, which direction is the absolute steepest way downhill. So by taking tiny, calculated steps in that direction, it literally descends the gradient toward a point of minimum error.
So how does it know for sure when it's found a valley? Well, first, it uses that derivative to find any point where the slope is 0. Where the ground is perfectly flat. Those are your candidates for peaks and valleys. Then, to tell them apart, it uses this other tool called the second derivative to check the curve's shape. If the shape is like a bowl, it knows it's found a local minimum, a really good spot of low error. It's an incredibly efficient way to find the best path down.
Okay, on to our final tool. We have a compass to set our destination, and we've got a steering wheel to find the fastest path. Now we just need an odometer to measure the total distance we've traveled, or the total effect of our whole journey.
And this is the job of the integral. An integral is this amazing tool for summing up an infinite number of teeny pieces to get a meaningful total. Just think about calculating the total area under some complex, curvy line by adding up millions of impossibly thin little rectangles. That's what an integral does.
And in data science, this is incredibly useful.
For instance, we often check how good a model is using something called the area under the curve, or AUC. This integral gives us a single, neat number that summarizes how well the model can tell different things apart. We can also use them to figure out the total probability of something happening. It basically gives us the big picture.
And you know, here's the most beautiful part of all of this. The fundamental theorem of calculus proved that our steering wheel, the derivative, and our odometer, the integral, are perfect opposites. They are literally two sides of the same coin, just beautifully connected.
So, let's put it all together. Let's assemble our complete AI toolkit. We now have the 3 core components that let a simple algorithm start to truly learn.
And here's how it works. The limits act as the compass, defining that ideal goal of 0 error. Then, the derivatives are the steering wheel, powering algorithms like gradient descent to find the absolute fastest path to get to that goal. And finally, integrals are the odometer, letting us measure the total performance with things like the area under the curve. This simple toolkit, this is the engine of modern machine learning.
Of course, this is really just scratching the surface. As Isaac Newton, one of the guys who came up with all of this, famously said, "What we know is a drop, what we don't know is an ocean." These simple tools open up a whole universe of complexity.
And that leaves us with a final thought to chew on. This whole idea of improvement through a series of tiny, guided adjustments. That's not just for AI, is it? So what else in our world, from our own personal habits to big societal changes, could be understood as a journey of infinite small changes?